So for this lesson, we're learning about triangulation calculations. So when we're trying to determine the distance between an object and a baseline, we are able to use a scale factor to then measure out on paper so that we can then calculate the paper measurements to determine in real life how far an object is from a baseline, from where we're standing. So in the examples in lesson 3.3, we're going to see that the first one, it's actually covered in the slides. However, we're going to go through the virtual workspace to understand how this triangulation calculation would work. So for the first example, to determine the distance of a ship from the shoreline, the following measurements are taken. So they have a baseline already. They measure it out to be 120 meters. And then they have two angles. The first angle is 75 degrees and the second angle is 65 degrees. So now our job is to use a scale diagram to determine the distance to the ship. So ideally you would want to work on this one on paper using pencil. However, if you do not have a protractor or a ruler handy, you can also use the virtual workspace to create this, which I have open on the right side of the screen. So on the first one, I copied and pasted the question into the workspace, and I've included all the information as well as the calculation for the scale factor of 20. So 1 centimeter on paper is going to be equivalent to 20 meters in person. So physically 20 meters distance-wise from where you're measuring on the shoreline to the boat that is out in the water. So the first step that we do is, well, we need to measure out and figure out, well, how long is the baseline? How long would it be on paper? So if the baseline were to measure in person 120 meters and we have a scale factor of 20, that means that on paper, the baseline would measure out to be 6 centimeters. And the way that we found that is we would use this scale factor of 20, and obviously we cannot draw out that large of a diagram. So that is why we use the scale factor. We're going to reduce the size, and then at the end, we are going to turn it back and convert it back into the meters measurement. So the first step would be to divide the 120 meters by 20. And this is what is going to give us the measurement for our diagram, our map on paper. So we have 6 centimeters as the baseline. And for the workspace, you're going to want to use the ruler and the protractor provided. Keep in mind that it's very important that you do not adjust the size of the ruler so that you can achieve the most accurate measurement as possible. So to get started, the way I achieved getting the blue lines is you can pull in lines and click and drag to measure out the 6 centimeter baseline. So I already have it drawn out here. So I'm going to just double check using the ruler given to me that it is 6 centimeters. You can see I'm using the side with the centimeters units. So I'm going to mark that down as 6 centimeters. Now the other information that they give us, and I'm just going to move the ruler over to the side because we don't need it for this next step quite yet, is we have two angles. We have angle A and angle B. So for the first angle, for angle A, we are going to use the protractor to measure out the 75-degree angle. So this would be before we actually draw these angled blue lines. We are first required to figure out, okay, well, where would I extend the line if it was about 75 degrees? So now that I have lined up my protractor, I'm going to move these lines out of the way just so that we can utilize the workspace given to us. We would take another line and we would want to match up with 75 degrees on the protractor. So just as a review for protractor usage, When you line it up, you're going to line it up with the baseline starting at 0. Now you're going to notice that there's the two sets of values, and that's to allow us to measure going this way in the counterclockwise direction and also measuring in the clockwise direction. Now when we're measuring the angle on the left side, we are going to be measuring the angle going counterclockwise. So that is why I lined it up on this side here. The perpendicular line at 90-degree mark would line up with the very edge of the line so that I can now trace all the way up to 75 degrees right here. And then you're going to use, if you were drawing it by hand, you would use a ruler, you would mark this spot out, and then you would connect this line here. Now, because we have it on the virtual worksheet, we don't necessarily have to do that. We just have to trace the line out so that it passes through this 75-degree mark here. And then we're going to then work on the other side. So the other side, we've got another line that we are going to draw out, but first we have to figure out, well, where is the 65-degree mark? So same thing, I'm going to zoom in here. We're going to line up the best that we can to get the most accurate result. So we've got the perpendicular 90-degree mark lined up with the edge of that baseline. And then I'm going to trace another line that is going to pass through the 65-degree mark. So like you can see on this side here, we are working clockwise now. So we lined up the baseline at the 0-degree mark as there is no angle quite yet. And then we are going to measure up going clockwise up to 60, up 5 more degrees, and here is the 65-degree mark. So now that I have my two angles drawn out, I can now map out where the ship would be. So in theory, the person that is standing on the shoreline would be standing on the baseline down here that measures out 6 centimeters. The ship that is in the water would be right where those lines intersect. So that's why I put this shape here. You can choose the shape of your choice. You can even find an image of a boat to put into your diagram. It is up to you. Now that I have figured out, well, this is how far out that ship would be, I can now go back to my ruler and measure out the perpendicular line. So you want to measure out the closest distance that perpendicular line could be traced from the ship back to the baseline. So I'm just going to rotate my ruler so that it's in the orientation that I need it to be. And then I'm going to try to line it up so that I have the 0 centimeters starting on the base. And I'm going to zoom in to get it a little bit more accurate. And as I trace up, you can see that we have 1, 2, 3, 4, 5, 6, 7, 8 centimeters. And I can see it's slightly past 8 centimeters. It's approximately 8.1 to 8.2 centimeters. So any of these two measurement values would be correct. You would see that in your slides for this lesson. We go with the 8.2 measurement, and I'm using 8.1 in this example to show that they are very accurate and close in measurement. So now that I have the actual measurement of the baseline, I draw it out here, or not the baseline, sorry, the perpendicular line. So if somebody's were to stand on the 0 centimeter mark and the boat was out in the waters at the 8.1 centimeter mark, now we have determined how far out the boat is from the shoreline. So now that I have the 8.1 centimeters, well, we need to change it back into meters, and we need to use our scale factor to do that. So now that we are going to use the map on paper, we're going to multiply it by 20 to give us our final answer of 162 meters. So our final answer is 162 meters. That is telling us that if we were to stand on the shoreline, that boat is actually floating about 162 meters out in the water. So just to recap, we started out by tracing out a baseline using the scale factor to reduce the real life situation onto a scale that would work on paper. And from there, we went about measuring the degrees for both edges. And once we did that, we used the ruler once again to trace how far out on our map on paper the boat would be from the baseline, the shoreline. And from here, we were able to measure out 8.1 centimeters. And we now need to convert it back into meters so that we have a real life measurement for how far out the boat is from the shoreline. And to do this, obviously the measurement is increasing. So now we are multiplying it by 20 using that scale factor we originally started out with to give us the final answer for the distance of the boat from the shoreline as 162 meters.